So I've set aside a little video. Hopefully this will be short, but just kind of like a review of reaction mechanisms and introducing maybe to some of you a little bit of new terminology. I'm not quite sure what everybody's Gen Chem background has been, and I do know that if you took Chem 32 at UVM, you covered kinetics in pretty decent detail. And those mechanisms, so a reaction mechanism is basically just a proposal of how a process might occur. We use that kinetic data along with thermodynamic data to plot a reaction coordinate diagram and sort of maybe feel out how a process might occur or speculate to a mechanistic pathway. So these are data-driven ideas. And in our version of general chemistry, we we make sure to very specifically let you know that a reaction mechanism can never be proven. It can only be disproven. And so, but we lean on these data to help us sort of understand how a process might occur so that we can get in there and sort of shamelessly manipulate the matter further in our syntheses. In organic chemistry, we use these data from general chemistry to sort of give us an idea about what groups are coming in at, sort of what angle or how the orbitals are overlapping, what kind of a group leaves, how can we set up our reactions to our favor, especially if there are competing reactions occurring. So before all of this happens, let's sort of just take a walk down Gen Chem sort of memory lane and get everybody on the same page. In the event that you took a general chemistry course, like maybe Chem 23 at UVM, that maybe went a little light on the kinetics, let's just say, hey, why did we make you learn that in the first place? Because in organic chemistry, we're not going to be calculating anything. We're just going to be using the information that we learned about it. So why do we make you learn about mechanisms in the first place? So this is basically just, I guess, a proposal about how a process might occur. It is data driven. So this isn't just something somebody dreamed up, right? I mean, that comes first in the scientific process, but then, we gather observations and rinse and repeat. So it's data driven. And we have to be mindful that it cannot be proven. So we never say things like this happens and we know this, blah, blah, blah. We don't know anything really at the end of the day. We just use data to help us sort of understand or, rationalize or reason our way through things. So cannot be proven, but we can disprove them. And I want to show you two reaction coordinate diagrams that will be helpful to us in this course. So the first one I want to show you is, again, we're going to be plotting energy versus, so increasing energy relative to the reaction progress. So I'm going to keep this to exothermic processes. Those are enthalpy favored processes. We know endothermic processes occur, right, where your system requires energy, and that's okay. At the end of the day, thermodynamics tells us that everything tends towards decreasing free energy, or delta G, if you remember from thermo, is minimized. but we're talking enthalpy here. So heat, right? Thermal energy. I'm going to keep both of these examples exothermic so that at the very least, these are enthalpy favored. And we're going to be talking about the kinetics and the thermodynamics on one plot. So we're going to go energy relative to reaction progress. And the first thing I'm going to do is I'm going to give you just a generic reaction. We're just going to say that A plus B is going to be transformed into AB. So A by itself, B by itself, we're going to form a bond between A and B. When you form a bond, you emit heat. So this is an exothermic process. Remember, all bond-making processes are exothermic. All bond-breaking processes are endothermic. So we're going to start out, since these are exothermic, with our reactants at higher energy than our products. So we'll just put those there. And then if you remember from general chemistry, we had this sort of bump there, and then down here, we had our products. So I just draw this gigantic x-axis for this tiny little reaction. Let me fix this for you. It doesn't really matter. We'll just keep it simple here. So there's our products. And what do we have going on here? We've got this area underneath this little curve here that in your general chemistry class, you probably referred to as the activation energy. So this little area in here, you remember, we called this E sub A. So the energy required, right, to activate those reactants as they make their way toward products. So at the top of this little thing, now in Gen Chem, you probably saw there was a little asterisk. In organic, we use this symbol. It means the same thing. It's our transition state. So this is where your reactants don't look like reactants anymore, but they don't quite yet look like products. And then here, do this in a different color for you, we have this drop in energy. We usually indicate this with an arrow going down. So this is your enthalpy. So delta H. So if you want over here, you could say that this is enthalpy, right? So some reaction progress diagrams will do delta G. That's fine too. I'm talking specifically about an exothermic process, so we're just going to say let that E stand for enthalpy, right? So delta H, the change in the enthalpy. We've got our reactants energy, and then we have the energy associated with our products. We have an exothermic process when this bond is formed, so we're saying that energy is being given off in the form of heat. So in other words, we have our delta H for an exothermic process is going to be less than 0. That is, heat is being given off. Or you could think of it like, hey, heat is a product, right? So A and B, we're just going to write down everything we know about this as we see it. A and B are our reactants. And then AB are, or is, I guess, the product. The other thing we know is, and I say we know in this instance because we're labeling the graph, E sub A is the activation energy. And if you remember from general chemistry, this speaks to the kinetics. In other words, the speed of the reaction. Delta H up here, our exothermic process, this speaks to the thermodynamics. So on this graph, we're looking both at thermo and kinetics. Or at least a piece of thermodynamics, right? We're not talking entropy here. We're not, in fact, the entropy is decreasing here, right? Because we're taking two things and we're consolidating them. So every time we do a synthesis, right, we're going to be dropping an entropy, which is considered undesirable thermodynamically, but it's enthalpy favored. So this very specifically is talking about enthalpy. Thermodynamics, as you remember, is all kinds of different things, right? And at the end of the day, the green light for a reaction is decreasing, free energy. So again, this is just a piece of thermo. E sub A, speaking to the kinetics, how fast is this thing going to go? The bigger that mountain is, the slower the reaction is going to be. That's going to be something that you're probably going to want to remember. So if you can envision a tall bump versus a small bump, right? The small bump, that's a faster reaction. The other thing we notice is that we have this little symbol here. This is speaking to our transition state. Sometimes called the activated complex. But I don't really like calling it that because it leads people to believe that it's something that you can isolate and look at. It is not. It's an imaginary, sort of like theoretical thing or spot in the reaction where your reactants don't look like reactants anymore and they don't yet look like products. It's this in between stage, right? And when you get to the top of that little mountain, then once you achieve that transition state, that theoretical place where you're in between reactants and products, then you're either on your way down if you have an exothermic process, right? Or you're on your way to products. So we have our transition state. And the other thing that we notice in this particular graph is that we only have one of these. So there's just one activation energy in this particular graph. Or one energy barrier. When you're looking at a graph like this, you can probably say to somebody, this process occurs in one step. And so in organic chemistry, we have a term for that. This is a one-step process. We call that a concerted process. We will be looking at, very specifically, we will be looking at certain reactions that will occur just in one step like that. And the kinetics will tell us that in the data that's derived from the kinetics will tell us which molecules are involved in that step. So the molecularity of the reaction, remember, like the concentration, if you change the concentration of one thing and you hold the other one constant and you notice a change in the reaction rate, if you take the other thing, change its concentration and hold the first thing constant and you notice a change in its reaction rate, then it's bimolecular, right? So that's going to be important to us in organic chemistry because when we set up our reactions, if there's a reagent that you use where its concentration doesn't matter, then you can use it in a wild excess, like as in use it as the solvent if it's a liquid, right, and your stuff dissolves in it, or use it sparingly if you, or stoichiometrically, right, if increasing its concentration isn't going to affect the rate of the reaction. If you find out that you have 2 or 3 reactants and only one of them is going to affect the rate of the reaction, then you can mess around with your reaction conditions such that you increase the concentration of just that one thing and use the other stuff stoichiometrically. So there's a whole bunch of information that we can get from these data. So again, the kinetics is not only going to tell you how fast this thing is going to go, but these little reaction progress diagrams are also going to give you some kind of a clue about the pathway by determining which species. So if you have just one species or 2 or 3 or whatever, are involved in what we call the rate determining step. So I should probably write out what that is. And we abbreviate that usually RDS. If you remember from Gen Chem, this is your slow step. So this is the rate determining step. In this particular plot, we have one step. So we're looking at a one-step process. I'm only seeing one activation energy, right? So that leads me to believe that, this is my rate determining step. It's the only step, right? But if there's multiple bumps, the slowest one will be your rate determining step. The whole entire reaction has to wait for that step, right? It doesn't matter how fast the other ones are. So this is going to be your slow step. And if you remember from kinetics, when you pluck apart your reaction, right, and you sort of propose like a general mechanism, and then you mess around with the concentration of each of your reactants, and you study the rate of the reaction, the slow step in your proposed mechanism is going to be your rate determining step. It's kind of how you can figure out like who's responsible for holding up the show, kind of a thing. As a synthetic chemist, you kind of want to know that information, right? So that you can mess around with your reaction conditions. So again, the higher that activation energy is going to be, the slower the reaction will be, or that particular step will be if you only have just that one. But what if you had more than one? What if you were staring at 2, for example? So here we have our increasing energy. We're going to plot that relative to our reaction progress. And we'll use the same reactants, but say, imagine we've got a couple of steps now. So imagine we have A plus B, and we'll keep it exothermic. But here we are, A plus B, there's their energy. And then we've got this situation going on. We've got this big bump, and then we have a smaller bump, and then we have our products. So here we have a couple of different peaks. We have our transition state for the first step. We have a transition state associated with the second step. And then we get this thing right here. The heck is that, right? That's a special little place. Let me color these in for you. So there's transition state 1. We'll say this is going to be transition state 2. And then we've got this thing. That is our intermediate. Do you remember from Gen Chem we talked about intermediates? If you were writing out a mechanistic pathway and you had something that you formed in the first step, so it was a product of your first step, but then it was sort of gobbled up and used as a reactant in a subsequent step. So it doesn't actually make it into the rate law or your overall reaction equation, but it exists in there fleetingly. That's an intermediate. So that's where we see that on the plot. Here we have, again, an exothermic process because our products are lower in energy than our reactants. So delta H, again, we can say this energy is related to the enthalpy if we like. For this process, again, delta H is less than 0, so exothermic. What else can we say? We can say that our activation energy for the first step is E sub A1. Activation energy for the second step, E sub A2. We can say that our first activation energy is going to be greater in energy than our second, which means that E sub A1 describes your rate determining step. Or in other words, the slow step in the reaction. Everything about this process, even though it's a two-step process, is being held up by however long it takes for that first step to occur. So whatever's going on there is taking some time, and you have to wait for that. And the kinetics data can help you learn, or at least gain some insight about who's involved in that slow step. You know, it may not involve both reactants, or it may not involve either reactant, right? It may involve like a third thing that you have to put in there. Whatever it is in your particular reaction, you get to find out by looking at that particular step. This particular transition state is for the first step or for the slow step. So transition state number 1. So when you're putting these reactions together, you have a bit of a clue because you know what you put in the reaction pot. And then you have a hypothesis. You think like, I think this is going to happen to this, and then whatever that turns into is going to react with this. Or these two things are going to come together and react this way. So you sort of like set yourself up, right, before you start the process. We don't typically walk into the lab and be like, hey, today's the day. I'm just going to blindly grab some stuff and throw it into a reaction vessel. You have a bit of a clue before you get going. So these reaction progress diagrams can give you some information about that. When we're looking at these different transition states, we can say, well, I think this is what's actually happening at the transition state. If I change the reaction conditions such that I favor transition state 1, or I can stabilize transition state 1, right? That's my slow step. Then perhaps then I'm helping the reaction along. What could I possibly do to make that particular activation energy lower? What if I gain some insight about what's going on in that first step? And I'm like, hey, I think if I add an enzyme or some other kind of catalyst, right, and shrink down that activation energy? Or what if I decide I want to just crank up the heat, right? So again, we start moving into, I have an exothermic process. Heat is actually a product. So, you know, once this thing achieves equilibrium, if I put heat into the system, I'm driving the reaction backward. You have to consider a whole bunch of stuff. But if you remember from Gen Chem, increasing the temperature of a reaction can, right, increase the rate. So you just have to kind of figure out what's going on. In this particular case, we see that we have 2 bumps in general. So since we have 2 activation energies, means we have a 2-step process. And again, our rate determining step is going to be that first bump because it's bigger, right? The energy barrier is larger. And then the last thing on this particular diagram is this little asterisk that I put in. And this is going to speak to an intermediate. So your intermediate is formed here. And then it's used in that second step, right? It doesn't appear in the products because it was gobbled up as kind of a reactant that was made in situ. So your intermediate is formed, and we use this word in, or these two words, in situ. So that particular intermediate is formed and it is a reactant in your second step, but it's not something you added to the pot, right? It's something that was generated in that first step by two other reactants, but it's necessary for that second step to occur. And then you don't see it after the reaction is over, right? So that's our intermediate. Okay, so that is sort of like the sort of recap of reaction mechanisms from general chemistry. Let's talk just a little bit about some terminology that you might not have heard in general chemistry and that we will talk about a lot in organic chemistry. So some terminology specific to orgo. We are going to sort of filter these reactions down into their components. So instead of memorizing reactions, organic chemistry sometimes leads people to believe they need to go buy a pack of flashcards and just memorize. You should not be doing that. There's too many reactions to memorize and there's no need, right? So instead, you look at a reaction and you're like, hey, I remember from general chemistry, I learned that on the left-hand side of the reaction, we typically are staring at reactants. And on the right-hand side, we're staring at products. We went through the different types of arrows that, what they mean and all that stuff, and the different symbols, right? So the delta symbol is like either a change in something or a difference in something, or it can mean heat, that kind of stuff, right? So you already have some of the symbols and terminology down, but in organic chemistry, we have a couple of other things that we like to talk about. And if you're looking at a reaction and you can find these two things, then you've already decided that you know, or you think you believe, how this reaction is going to go forward. And that's sort of a big help. So the first thing that we like to talk about is identifying the electron-rich species. In organic chemistry, we are basically talking about a soap opera between two or more um, species, one of which is deficient in electrons and the other one is rich with electrons. And it's just going to be like the relationship between these, right? So some electrons rich species is going to come along and it's either going to use those electrons to attack the electron deficient portion of another molecule, or it's going to be, those electrons are going to be used to rip a proton off of another species. But we have a term for this electron-rich species. We call this a nucleophile. So in other words, so philic means loving, right? This is nucleus loving. And conversely, we have another species in the pot, the electron deficient species. And we call this an electrophile. And that basically to us means electron loving. You either have a bona fide positive charge on something, right? So a formal charge on something, or you have a partial positive charge on something, on a molecule, and there are two electrons coming from another species, like a heat-seeking missile for that particular portion of your electrophile, right? Or you've got a partial positive charge on a hydrogen. So we have an acidic hydrogen somewhere on another molecule, and the lone pair of electrons on the nucleophile are going to come in, or some pi electrons, right? So from an alkene or an alkyne are going to come in and snag either that acidic hydrogen, or they're going to attack that electrophilic site. So it's really kind of like a soap opera between these two species. We have an electron rich species, we have an electron deficient species, and they're going to intertwine. So typically, and in this class, most of the time, we will push electrons two at a time. So a lone pair. Or pi electrons, so electrons in a pi bond. So a lone pair on an atom like a nitrogen or an oxygen or a sulfur or whatever, or electrons in a pi bond. Sometimes you can push one electron at a time. And when that happens, we call that a free radical transformation. So typically we're going to be pushing two electrons at a time. And when we do that, we use a double-headed arrow. So for this, in our proposed mechanism, we use a double-headed arrow. So a curved arrow, right? So in parentheses, I can do an example there. That's what that looks like. And you have to be mindful that we are pushing this arrow from the nucleophile toward the electrophile. We are not pushing these electrons out into outer space. So very often when, and this won't be in this class because we're not testing you on the mechanisms, like you don't have to regurgitate the mechanisms, but in, another organic class where we ask them to write out the mechanisms, we'll see students putting, these arrows going off into outer space because they're just not completely sure where it's supposed to attack the other molecule. We are pretty specific with these double-headed arrows. So two electrons are coming from the nucleophile and they're attacking a very specific spot on the electrophile. The other thing that you have to be mindful of is that those arrows are always going to go in the direction of the electrophile. So we're coming from the thing with electrons and we're moving toward the thing that's deficient in electrons, not the other way around. Protons don't attack things. We attack protons, right? And then so we'll put like a little star here. If we are pushing a single electron, otherwise known as a free radical, we use a single-headed arrow It kind of looks a little bit like a fish hook. So that right there indicates we're pushing one single electron. So we will probably do a couple of reactions where we're pushing radicals around, and I'll show you those mechanisms just so you can kind of like get an idea about how we think something might happen when that occurs. But for the most part in this class, everything is going to be two electron pushing, right? So two electrons at a time, those curved sort of double-headed arrows. And the last thing in this video that I wanted to talk to you about is some common mechanisms. So we're going to talk about 4 common reaction mechanisms. This is our abbreviation for reaction. So if I keep doing that and you're like, why is she doing that? That's what it means. So 4 common reaction mechanisms, or 4 common processes that we're going to notice in this class. The first one, might as well start out with just the Gen Chem review. Again, we're going to be exchanging a proton acid-base style. So we can exchange a proton, and I'll put in parentheses acid-base style, because we will have another common reaction mechanism where this isn't done like an acid-base reaction. But this one will seem probably familiar to you because you did acid-base chemistry in Gen Chem. So I'm going to use an organic acid here. Do this in a different color. We'll take just a generic carboxylic acid. So we'll put R for rest of molecule over here. Here's the carboxylic acid portion of this molecule. And in this video, and pretty much only this video, I'm going to be drawing out all of the lone pairs, even if I don't use them. Typically in organic chemistry, when we're drawing out our reaction mechanisms or proposing our reaction mechanisms, we don't draw all the lone pairs on the heteroatoms or whatever. We call heteroatoms or anything other than like a carbon, right? So unless we're using those lone pairs, we don't typically draw them in because it can be a little annoying to put all the dots in. But for this, I will, just this video. So we have a carboxylic acid here. And our acidic hydrogen is sitting right here. So we went over this in our review. That's going to be the acidic hydrogen, right? So the electrons are not being shared super equally between that oxygen and that hydrogen. There's a dipole moment going up through the carbonyl. It puts a partial positive charge on that hydrogen, and then along comes a base. We'll use our generic hydroxide. The negative charge is actually on the oxygen, but again, we typically put our charges up to the top right. And then we're going to use our curved arrow to take 2 of the lone pair, or 2 of the non-bonded electron, I should say, 1 lone pair of electrons on the oxygen. And we're going to push that arrow toward that partially positive charged hydrogen, or the acidic hydrogen on the carboxylic acid. So here's your base, our generic base there. When that base takes that proton off, or I should say that hydrogen is removed from the carboxylic acid, right? That acidic hydrogen, the electrons that are bonding the hydrogen to the oxygen are given to the oxygen. And we use another arrow to show that. They're being dumped onto that oxygen. If we're dealing with, well, we have a strong base here because hydroxide is pretty strong. If we're dealing with a weak acid or a weak base, we typically use our little equilibrium arrows, but I'll just use that generic going forward to products arrow. What we get on the other side of this is the conjugate base of the carboxylic acid, and it has a name in general. Now there's a negative charge on that oxygen, and this becomes a carboxylate. And the conjugate acid of your base obviously is just water, right? But this will be your conjugate acid. This is your carboxylate. which is the conjugate base. So this curved arrow is going to be showing that we're pushing 2 electrons at a time, right? So we're exchanging a proton, acid-base style. You can also exchange a proton and then you can follow that up by the addition of a new group. So that's, I'm going to just pull that out as a separate reaction. So we can do a proton transfer. Followed by the addition of a new group. So this will be a token reaction for alkenes and alkynes. We'll give an example here where we're going to take an alkene, and we'll do a separate video on very specifically characteristic reactions of alkenes and alkynes. But we'll just show you here, we're going to do a proton transfer, and we're going to follow it up with the addition of a totally new group. So there's your alkene. Now, remember when we said the nucleophile can be either a species that has a lone pair of electrons on some atom, and those electrons can be used, right, to attack an electrophilic site on another molecule, or they can be the electrons involved in a pi bond. If you remember from Gen Chem, when we're forming our bonds, if you have a double bond, it's made up of a sigma bond and a pi bond. The pi bond comes from those unhybridized p orbitals, and the orbital overlap isn't super awesome. So the bond is weaker. The sigma bond is stronger. So the electrons that we use, right, from the double bond are going to be the electrons involved in the pi bond. At the end of the day, we kind of don't care because you're not drawing out the pi bond, you're just drawing the double bond and using that as a source of electrons. So in other words, I'm going to add a source of an acidic hydrogen in the form of hydrobromic acid. And what I'm going to do is I'm going to attack. So here is my source of H plus and also the new group. I'm going to show you how that works. The new group that's going to be added is going to be the bromine. But right now, it's tied up in HBr. So the hydrogen is covalently bonded to the bromine, and we are going to take the electrons in this double bond, and we're going to use them. Let me give you a better arrow than that, sorry. So we're going to show that we're pushing electrons from the double bond. Again, we're going to use those pi electrons, right, to attack that partially positive charged hydrogen. When we do that, we're going to break this covalent bond by relinquishing the electrons in the covalent bond and giving them to the bromine, which will become bromide. So what we get is this. So I'm still going to draw this double bond or this single bond in here. So you see we just broke the double bond, right? And I'm going to put the hydrogen on that terminal carbon. When we get to these reactions, I will tell you why I chose that particular carbon instead of the one in the middle. The one in the middle, because I use the electrons in the double bond, right, to form a bond between this carbon and this hydrogen. So that's this over here now. I have removed electron density from this carbon, and it now has a +1 charge, a bona fide +1 charge. But guess who came off in the last step? Bromide, right? And it has a lone pair of electrons now that can be used to attack that electrophile, that positively charged carbon. And when that happens, we form a new bond between this carbon and that bromine. We've effectively created a new bond in a totally different molecule. So we have a proton transfer followed by the addition of a new group. This is one of the characteristic reactions of alkenes and alkynes. We call this an electrophilic addition reaction. And we'll go into detail about this in another video. The third type of common type of mechanism or reaction mechanism is where we're going to break a bond to form a stable ion or molecule. So you just literally saw that in the last example reaction, that intermediate step there where the bromide attacks the positively charged carbon. We've actually formed what we call a carbocation. And the more stable that thing is, the more quickly it will form. So here we have bond breaking to form a stable ion or molecule. You're not going to be breaking a bond to form something that's more reactive than what you started with, right? So that's something you might want to remember. When we start talking about the awesomeness of a leaving group, incidentally, that bromide, that Br that took off in that last reaction, that's what we call a leaving group, is taken off when that molecule is attacked. The more stable that species is after it leaves, the more likely it is to leave. So when we break bonds to form stable ions or molecules, that is a sort of common characteristic reaction mechanism. You won't be seeing a bond breaking to form an unstable ion or unstable molecule without some serious help from your reaction setup, if at all, right? So these things tend to go spontaneously when the products are lower in energy, right? If something is unstable or reactive, it's higher in energy than it was before you started, right? So that's unlikely to happen. Not impossible, just unlikely. So this example could be like if I took T-butyl bromide. So if I have something like this, and this bond just slowly begins to break all by itself. This is actually a slow step. So we were just talking about reaction progress diagrams. This would be considered the activation energy for this would be the tallest bump on that particular plot, is the breaking of this bond to form what we call a tertiary carbocation. So when that bond broke, we pulled electron density away from the carbon. Bromide took off with those electrons, and we have what we call a tertiary carbocation. Tertiary carbocations, of all the possible carbocations, primary or methyl primary, secondary, and tertiary, the tertiary carbocations are the most stable. The groups in that particular carbon is considered a tertiary carbon because, again, it has 3 R groups hanging off of it. So those 3 R groups, those 3 substituents, can help sort of like infuse electron density in toward that formal +1 charge on the carbon, and it helps to stabilize it. So tertiary carbocations are more stable than secondary. Secondary are more stable than primary, and primary are wildly more stable than methyl. Methyl carbocations are so ridiculously reactive that they generally don't form. This will be important for us to remember as we work through the course. Tertiary carbocations are the most stable. And then the last common sort of reaction mechanism that we can talk about is if, and this one is, in my experience, the most difficult for students to see because it doesn't involve the creation of a charge. It sort of quenches a charge on one atom and creates a charge on the other. And so it's a hard thing for students to envision happening. It's a rearrangement. Rearrangements can be a little difficult to envision. They don't seem like they occur for any specific reason, but when they do, we can rationalize them, or attempt to anyways. So we have the rearrangement of a species to form something more stable. So say you have a reaction that produces a primary carbocation, and you're surprised that because you envision that reaction mechanism has to go through a primary carbocation for it to occur, and all of a sudden you have a reaction that occurs, and you're surprised by the product that you get. So the group is either on a different carbon or some other group has migrated, and you're like, well, what the heck was that all about? Well, a primary carbocation is less stable than a secondary carbocation, which is less stable than a tertiary carbocation. And if the molecule forms a primary carbocation, has the ability to trade a substituent, right, or rearrange itself, or even trade a proton, do like a proton shuffle, right? We call that like a hydride shift, where we're just going to swap an atom over and sort of quench the positive charge on the primary carbon and create a secondary carbocation or a tertiary carbocation, then that will happen. And again, those are a little harder to see. I can give you an example of a methyl shift. So if we start out with something, I guess, that looks like this. So say you have this that you're starting out with. You have a secondary carbocation here, right? That carbon is effectively bonded to two R groups and a hydrogen. What we can do is we can shift a methyl group over here and create a tertiary carbocation, which is more stable. So this methyl group went over here. When that happens, this carbon, but notice the difference. That's a tertiary carbon. It has 3 R groups attached to it, whereas the other carbocation only had 2. So over here, we have a secondary carbocation, and over here we have a tertiary. And this is more stable. It's lower in energy, in other words. Okay, so those are the 4 typical reactions, or the sort of generic reaction mechanisms that we will talk about throughout the semester. They will get specific to the specific functional groups that we're talking about, but in general, these little four umbrellas of reaction types are what you're going to see the most of this semester.